What we're looking at today is introducing the concept of optimization. Okay, optimization. When we say something is optimal or optimized, what do we mean? Huh? Improved? Effective?
The best.
Okay, the best. That's probably the optimal answer so far. Okay. Yeah, when we're trying to optimize something, we're trying to find the best solution for that situation. Okay? So that's one of the things we're going to be dealing with. We're also going to be looking at the concept of derivative as a rate of change in a little more detail here. Okay? So, derivative as a rate of change. And I have some examples here. Okay? And typically when we think rate of change, we're always thinking about like position is our function and the derivative is our velocity. Okay? But rate of change does not have to be just that. Okay? You can see here we can deal with things like cost. If we have a cost function, a business term is marginal cost, and that's the unit price. That's the unit price if we produce a certain number of units. Okay, and you guys are probably familiar with this somewhat. You know, if I'm only building 5 cars, it's going to cost me a certain amount because I have to pay someone to do it. I have to get equipment. I have to have a facility. I have to get the materials for those 5 cars. But as I produced 100 cars, my cost per car actually could go down for a number of reasons. For one thing, there are certain fixed costs. Like I've got to have the facility. There are certain things like electricity and insurance, all those things that aren't going to change no matter how many cars I produce. Okay? There are other things like materials. If I'm buying just 5 of something, I may get one price, but if I'm buying 100 of something, I may get a better deal, buying in bulk. That's why big manufacturers can produce things cheaper than a small mom and pop type of place, okay? But that's what marginal cost is, and we want to figure out like the optimal, how many units should we produce to give our optimal marginal cost. We can also look at area or volume growing. Okay. In fact, if we go even further, which we aren't going to end up doing, we end up with looking at related rates. And that's something in calculus that is not part of what we are going to do, but it is an interesting application where we see how as the rate of something is changing, let's say you're draining out a pool. Okay, and the water is pouring out of this pool at this rate, we can then see what the rate of the level of water is dropping in the pool, or the depth of water. And where it really gets interesting is if your pool isn't rectangular, if it's like cone-shaped or you have different shapes, you can look at how the volume is changing, or if it's sloped from like a shallow end to deep end. It's going to be different as you get down to the deep end and whatnot. So it's interesting there, different growth rates, but also things like population. And I'm not just talking about like population of a city, although that is one example, but say population of a bacteria or something like that. Population of people pouring into a stadium to see some kind of an event. We can look at different rates, growth rates, modeling things, and figure out, okay, when is our growth rate going to be the greatest? In other words, when are the more people going to be showing up at once? That's when we need to have more people at our different gates, letting people in and stuff. Okay? So there's a lot of different modeling that we can do, and then the derivatives give us those rates. that we can then apply with. Okay, so let's look at a couple of examples. Here's an example dealing with costs. The company designed this model to illustrate their total costs of production. Okay, and they did it in terms of the number of items. So they went through all their expenses and they realized that $2,200 are fixed costs. In other words, we're going to owe this much every day or spend this much every day whether we produce anything or not. Okay? And then there were basic raw materials. It costs $5 for every item that we use just for the materials to produce it. Okay? And then the labor. Now this one is a little more complicated because you may have a certain point where people start to get overtime or if we only produce this many, we only have to have this many people here, so we're not paying as many people. Okay, so there's all kinds of things that go into this kind of a model, but what we can do here is we can find a marginal cost function by taking the derivative. Okay, so C prime, our marginal cost function, C prime of x, is going to be 3 times the 0.00013, so 0.00039 x squared, plus 0.004 x plus 5. That's going to be our marginal cost. Okay? Now it says find the marginal cost when 150 items are produced. So what are we being asked to find?
Plug in 150.
Yeah, plug in 150. Okay, so C prime of 150. And you'll want your calculator for this, so get those out if you don't have them out already. So 0.00039 times 150 squared plus 0.004 times 150 plus 5. Okay, what'd you get?
14.375.
14.375. Okay, now what does that mean?
It costs 14.375
A day.
at 150. When it agrees 150 like per day.
Okay, let's keep going. That it costs. $14.375. Well, that's dollars, right?
Mm-hmm.
Okay, we'll assume this is in dollars. So $14.37.50. Now, is that our total cost of production?
That's the marginal cost.
Okay, so what does that mean? It costs that to produce what?
150 items.
All 150? Each one. Okay? To produce each item when we produce 150. In a day. Okay? That's what that number is telling us. Okay? If we were producing 160, it would be a little bit different. Okay? That's why we have this function. Now, part C is kind of interesting. Okay? This is an exact cost. Alright? The cost per item when we produce 150. What they're telling us here on part C, find C of 151 minus C of 150. What they're actually having us do here, C of 151 minus C of 150, that's going to be the cost of the 151st item we produce. Okay? So producing one more should cost us about how much?
$14.
$14.37.5, right? It should be around there, okay? Now, this is where we get the difference between instantaneous rate of change and average rate of change, okay? So, because we're subtracting here, the cost of producing one more will be slightly different because the instantaneous rate of change is changing, okay? So, this is the cost of the 151st item. Okay? So, what do we get when we plug in 151 into our original function?
3,448.18. Should I go for there or?
We can round to the penny, so it's 0.1,
then.
0.19, okay? And the 150th item?
Working on it. 3,433.75.
And what do you get when you subtract those guys?
Let's see.
Looks like
14.44.
14.44,
Yeah.
That sounds right.
okay? And that's
Checks out.
pretty close, yeah. Okay? It's pretty close. So this would be an estimate of the marginal cost. The previous one is exactly what the marginal cost is when we produce 150. Okay? Alright, so that's just one example here. Another example, I'm intentionally doing ones other than motion here because I want you to see how these can change. Alright, let's think about this one. Find the rate of change in the area of the triangle as theta changes at the time when theta equals 60. Okay, so here's what's happening here. This is kind of interesting. Alright, we have these two lengths. One's 10 centimeters long and one's 12 centimeters long. Okay? And if we make the angle smaller, okay, and we still have 10 and 12, you know, here's with the smaller angle. Okay, obviously the area there is going to be smaller than the area when it is how it's drawn, right? And if I extended the 12 and made the angle bigger, that's about right. Okay, and I made this angle bigger down here at 10 centimeters. Again, the lengths are still 12 and 10. Notice this triangle is going to have a bigger area than the one that's drawn, right? What's going to happen though as I make theta bigger and bigger and bigger? What's going to happen to the area? Huh?
Like get bigger.
It'll get bigger. Huh? What if I keep making it bigger? Like if I made 12 go like this and 10 go like this.
Bigger than at one point it starts to get smaller.
Yeah, at one point it's going to get smaller. Okay? So there are a couple of things that we can do here. One, we can find the rate of change when theta is 60. Okay? And let's do that. We can also do something else on top of that that we'll look at when we're done here. Okay? Let's get rid of, whoa, not all of that.
That building's pretty good.
Alright, so before we can actually figure out what the rate of change in the area is, which we need to express the area as a function. Now, since we want to look at as theta is changing, we should express our area as a function of theta. Okay? Now, here's where, if you were stuck, you would want to look at the formula booklet. Okay? But can anyone remember how we would find the area of the triangle if we're given this stuff? We have two sides and the angle between them.
Side angle, side.
It's side angle side. What's the formula? Do you remember?
No.
Something with,
It was like cosine.
no, I don't.
It used some trig.
Yeah.
Well, let's think, because it's been a while, so if we don't remember a formula, we can always rederive it, right? That's what's great about math. It helps those of us who have terrible memories, like me, okay? So, I know that the area of a triangle is base times height divided by 2, right?
Mhm.
Base times height over 2. So let's make 10 the base, and then this will be the height, okay? That'll be the height. So, my base is 10. The height, I don't know, and that's 2, okay? Well, how would we figure out the height in terms of theta?
Well,
SOHCAHTOA, alright? Yeah, I have the height and I have this 12 over here. If I'm looking at this as a right triangle, because the height is perpendicular to the base, what trig function could I use?
so, 10. No, wait. Oh, that's hypotenuse.
I can't use the 10 because the 10 is this whole thing.
And
What?
it's-
Sine.
Sine,
That's the
okay.
hypotenuse.
Which would be opposite, so h over the hypotenuse 12.
H over 12. So what does H equal?
Sine theta over
12 sine theta.
12 sine theta. Okay? So, now I plug in for H. I have 10 times 12 sine theta over 2. That's going to be 60 sine theta. So guess what? Now I have my area as a function of theta. Okay? By the way, the formula that we just derived, if you were to use A and B instead of 10 and 12, okay, we would have the 10 was our base, the 12 was the A, and we have sine of theta. It's 1/2 AB sine of theta.
Oh,
1/2 times A times B times the sine of the angle between them.
well, what do you know?
Okay? Now that formula is in your formula booklet, which is nice, but even if there's something that's not, you can try to rederive or figure it out a different way. Be creative, okay? Be flexible with what you're trying to learn. Alright, so anyways, now we have this. If I want the rate of change, what do I have to do with this function? Do the derivative, okay? So we're going to do a prime of theta. What's the derivative of 60 sine theta?
Be just 60 cosine
60 cosine theta, yeah. Derivative of sine is cosine, so 60 cosine theta. And if I want the rate of change when theta is 60 degrees, that means I want a prime of 60 degrees. Okay, so 60 times cosine of 60. What's cosine of 60?
Oh, this is in degrees too. Wait,
It is.
5?
Huh?
Negative.
yeah.
Come on, why are we using our calculators? Come on. We know our unit circle.
Mr. Nixon, I'm
Wow.
sorry.
It's a half. Cosine of 60 is a half.
I'm sorry. Mr.
So our rate of change, now here's the deal, okay? You got to be careful here. This is 30. What are the units of measure?
For area? Centimeters
So-
squared.
This is a rate of change, something per something.
Is it centimeters per degree?
Close.
Centimeters squared per degree.
There we go, all right? This is centimeters squared per degree. Now, how do we come up with that? Let's look at this. Remember, slope is rise over run, okay? The rise are the y's, the y coordinates, In this case, the y coordinates represent area. What's the unit of measure for area? Centimeters squared. Okay? The area was in centimeters squared. The angle here is in degrees. Okay? So if I'm doing a rate of change, area over degrees, area over the angle, the area is in centimeters squared, the degrees are the denominator, so it's centimeters squared per degree. So at this moment, the area of the triangle is growing 30 centimeters squared for every degree that the angle is growing. Okay? Now, one other thing that we can do is we can actually look at optimization. Optimization would be finding the best solution, like we said before. And in this case, the best, I would say, would be the largest area. Okay? If I'm trying to find the largest value of a function, what am I going to do?
Max.
Yeah, I'm trying to find the max. Find the maximum area okay? So how do we find maximums, guys?
Define critical value.
Sign them.
Silent ones, okay? How are we finding a maximum?
I was kidding, guys.
We had 2 quizzes over this kind of stuff. How did we find maximum points?
Wait, second year.
Y?
Huh?
That Y number?
It's the y coordinate, yes, but how did we find what that was?
So, wait, it's the
What should he?
derivative of 0 and
The derivative
x equals 0.
is 0, yeah. Where is the derivative 0? Okay? So now think with me here. You need to get a range of values that are possible for theta. What is possible for theta? What's the smallest theta could be?
1.
0.
Okay, it's got to be bigger than 0, right?
Yeah.
Okay.
Okay, yes.
If it were 0, what would the area equal? If my angle was 0, what would the area be?
0.
0.
Yeah.
You don't have a triangle anymore, right? What's the biggest it could be? Or it has to be smaller than
180.
180. If I made it a full 180, again, I wouldn't have a triangle anymore. I just have a little line, and I wouldn't have any area, okay? So, I'm going to find the maximum area between theta and 180, 0 and 180. So, I set the derivative, 60 cosine theta, equal to 0. So that means cosine theta equals 0, which means what does theta equal?
0.
No.
No.
Oh.
Unit circle.
90.
90.
Yeah.
So guess what? Making a right triangle, notice the 60 really didn't matter because you divide by 60 it's 0. Okay? So if you make a right triangle, that gave us the maximum area. Okay? And notice this gives a maximum area of 60 times sine of 90. What's sine of 90?
1.
Thank you.
Let's go.
So 60 times 1 is 60 square centimeters. Alright? So that's the biggest triangle that you can make with sides that are 10 and 12. Okay? Would be that right triangle. Okay? So, those are 2 things that we could do. We could see the instantaneous rate of change at a particular angle, in this case 60, Or we can figure out, hey, what angle would we have to make it to give us the maximum area?
And then after that, after it's 60, after that, the derivative will be negative the entire time for the rest, right? Because it's decreasing.
Actually, yes. If we were to do a sign diagram based on our derivative, cosine, think about it, cosine's positive in the first quadrant, it's negative in the second quadrant. Yeah, so if you did a sign diagram for this, okay, A prime, we'd have here at 90 degrees, it would be positive and then negative. The area would be increasing until we hit that 90-degree angle, and then as we got into an obtuse triangle, the area would start to decrease.
You know what that looks like?
Huh?
Looks like a max.
Okay, there is a max there. All right.
You're killing it.
I can't wait for
All
Daniel
right.
to hear that. Hey Daniel!
Okay, so we've got some practice here. We got some different practice problems. Listen, take the time. One thing I will point out, just a formatting thing. Notice the units of measure here, kmh negative 1. What something to the negative 1 power is over.
Right.
So
why would they do that?
that's the same thing. I don't know why they didn't just write it this way. This is kilometers per hour.
If we see
Okay.
that, if we see that in a question though, should we, and it's asking us to answer, should we give our answer in kmh to the negative 1?
I don't care. If you write it as km over h, that's the same thing.
Okay.
So if you're familiar with that, but just understand the negative 1 has nothing to do mathematically with the formula or whatever.
Gotcha. Yeah.
Okay. So we have that problem and a couple of other examples here that you guys can try. Okay? All right.